wait a couple minutes.
Oh, we wait a bit? I'm going to still pull this on a little bit here. Look, I have a pointer here. You said you're going to wait a few minutes?
No, actually,
Or
we can get this underway. Hello, everyone. Thank you all for coming. My name is Tobias Hollerer. I'm a professor in the computer science department, and it's my extreme pleasure to welcome and introduce to you Dr. Matthias Nießner. Matthias is professor in computer science at the Technical University of Munich, where he leads the visual computing lab. And before that, he was a visiting assistant professor at Stanford University. He obtained his PhD 10 years ago or so at the University of Erlangen-Nuremberg in Germany. Matthias is extremely prolific, one of the most prolific and successful people I know in the field of computer vision, graphics, and machine learning. He's publishing in the most high-profile venues. For example, I just did a count over the last 2 years. Matthias has 13 CVPR papers, 13 more ECCV, ICCV papers, 5 NeurIPS papers. I mean, this is extraordinary kind of productivity and impact in that field. So extremely impactful in terms of like what other work is following in these footsteps as well. In years before that, he has also had great SIGGRAPH presence with a total of 25 transaction on graphics papers to his name. And I heard that he is this year coming back to that, so we're looking forward to SIGGRAPH papers this year as well from his group. So without further ado, let me give a big welcome to Matthias Nießner.
Yeah, thanks, Tobias. It's a real pleasure to be at UCSB. In this talk today, I'm going to talk about photorealistic reconstruction. And when I say photorealistic reconstruction, of course, there's different domains where you would apply it. Like for people, you can apply it for environments. In our group, we do kind of both. But in this talk, I'm mostly going to focus actually on humans. And when I say humans, I would love to get photorealistic avatars. I would love to have this conversation here that we are having virtually, but with the same experience. And this is not a new idea, of course. So people have been trying to do this for quite a while. In this context, people have been looking at faces for quite a while. So looking at face models is actually something people have been doing for a really long time. I mean, this was a paper that we did in 2015, but like the first works on like blend shapes and parametric face models were actually done like in the 90s, in the 80s even. And when we're talking about parametric face models, mostly the application here at the beginning was mostly for video games, for movies, for animation. And the idea there is basically you're mapping a 3D mesh of a face to a lower dimensional parametric space. And these parametric spaces, such as blend shapes, you can see those ones here. These are all these sliders that we have here right now. These are our parameters. One of them you just saw was the rigid pose, obviously. And if you're changing some of them here around, you see that the shape identity can be parameterized with a couple of coefficients in order to control the shape of the object. You can also control the appearance of the object. So in this case, we have an albedo map encoded in this representation here. And you can control it by just changing a couple of coefficients here. You can do the same with expressions. You can, control it. You can even change illumination here. So this is a very simple spherical harmonics model that we've used. And this is something that has been the standard in computer graphics for probably the last 20 years, these kind of models. Blend shapes is probably the most prominent example of what people are using. And one big question is, how do we actually compute these face models? And this is what I would like to dedicate this talk to. So this is something that people like this famous Bluntz and Fetter paper in the 90s, I think, they were one of the first that did this. And what they're doing is basically they're going ahead and scanning a few hundred people, specifically the faces with with high-end scanners, and then they fit a topological consistent template to each of these scans, right? So you have like one template mesh, then an artist model, you fit it to all of these scans with a non-rigid registration, and then what you do is you computing basically, so you have like one vertex, right, that is fitted to, let's say, 100 faces, and based on this distribution here, you're just computing a PCA basis, and the PCA coefficients is this low-rank approximation for identity and expressions and albedo, that is then parameterizing your model, right? So you have the eigenvectors are your basis functions, and your coefficients are essentially your phase parameters. And this is the model then. It's very straightforward. It's a linear model, right? It's very easy to evaluate. And you can go from like a couple of parameters, like tens of parameters basically, to a relatively complicated 3D model. And why do we do this? Well, we do this because at test time, then once we have created such a model, we want to fit this prior to some input data, right? So we want to, for instance, give me a point cloud, and from this point cloud, estimate these coefficients that I'm having here. And yeah, in most of our work, we've used like a couple of these coefficients, right, for geometry, albedo, and expressions and illumination and pose. And then we have a non-linear least squares optimization problem for the most part, where we say, well, please optimize. Like this is RGBD data from a Kinect, right? So try to make sure that every pixel that I'm projecting from my mesh that I have right now, if I'm projecting this one to these inputs, I want to make sure I'm optimizing for these optimal parameters P. And in like 2010-ish or so, like there was like phase shift, which was very big. This was what Apple bought eventually, and they put it on the iPhone. They use only depth data. This is the reason why they wanted a depth sensor originally in the iPhone, right? But it turns out you can do this pretty well actually just with RGB as well. If you have a good parameterization of your albedo space, you can texture it, right? And then you can do the same thing on RGB. And this was a relatively popular paper from our group, this face-to-face paper, which got quite an attention. You could actually go ahead then and track from videos very robustly these face models. It was very robust towards outliers, and you got pretty good 3D reconstructions over time from these face models. And then you had these fun applications, what we did in face-to-face, right? You can then use this to do facial reenactment, take here an input, and then reanimate like a video as an output. And yeah, now everybody can do this with neural networks, but in 2016, this was a big deal that we could do this in real time by just reconstructing models. Now, these PCA-based models are great, and I still think PCA is a very fantastic mathematical formulation that we can use for all kind of low-rank approximation problems. But this is how the model looks like. It's, if I show this to my family, they're not going to be so happy with me because they think, well, I'm just drawing a bunch of nice comical sketches, but it doesn't look very realistic at this point. So they lack detail, and they only cover a small region of the face, right? And this is the thing what we wanted to fix. And well, how do we fix it? Well, the first thing what we wanted to fix is the detail part. The detail part we want to fix by replacing the PCA. The PCA, by definition, is a least squares optimization, right? That unfortunately doesn't have a lot of detail, because what we do is we're taking the highest variance first. So we want to change the PCA with a nonlinear model. And since we don't know which nonlinear model we want to use, we simply learn these models. And this is what neural parametric models are doing. So here the idea is now, instead of having a PCA-based approximation, we're using an MLP with a latent code. And this latent code can be parameterized, one part by a shape MLP, and the other part by a pose MLP. So you can kind of do the same thing what the PCA has been doing. You want to disentangle these things, but it's like a shape autoencoder, right? It just gets in a coordinate, and it tells you for this coordinate what the respective output would be, and the parameterization of the space is done by a latent code. So it's relatively easy. It's just simple autoencoder style, or autodecoder style in this case, for the latent code. And then at test time, what you do is, right, like, so the parameterization, like what were the eigenvectors before, are now MLPs. They are stored in the weights, and the coefficients are our parameters. This is our latent codes, and we can take these latent codes and fit them to some targets. So now we can, again, at test time, we take a bunch of like point clouds here as input. So this is just for points. This doesn't have any RGB. And then what we do is we optimize essentially for the shape code that is shared across a sequence. We optimize for pose codes that are per frame basis, right? And then we can take a sequence of point clouds, in this case of depth frames, and we can fit this model to that. And then, in practice, this looks like this. So this here in the middle was our model. This was a paper from 2021. It's already a bit outdated. There's better models right now than choosing just a naive MLP. You can do much fancier architectures here. But you see a bit of a comparison between, these are human models now. This is basically, the simple model is a PCA-based model, right? This is what you can do this way, and then we get a lot more detail if you're using these neural parametric models. So now the big question is, we wanted to make that kind of stuff work on human faces. So how do we do this for human faces? Well, for human faces, I've shown you a couple of examples already what parametric models actually exist. And you can use those to fit them to point clouds as well. So I hope you can see this, that there's like, this is our little point cloud of a face. It's about 10,000 points. It's not that detailed, it's reasonable. And if you're taking a basal face model that's very popular in the community there, that's a PCA-based face model, you can fit it to those points. Looks like that. Doesn't look terrible, but it's just the face. Then people have done Flame, which is also very popular, also PCA-based, has a little bit more. And what we wanted to do is more like something like that. So we wanted to have hair, we wanted to have, well, the mouth interior to a reasonable degree, and we wanted to have just a lot more facial details. And this is what we developed in the last year. And the way we did this is we actually trained these neural parametric models specifically on face data. But it's not that simple. So we had to think a little bit about how we make this actually work to achieve a fidelity like that. And the first thing we had to think about is what data do we do? So we started with a bunch of 3D scans that were taken to have high quality data on 3D heads. And these ones captured both hair and they captured like pretty well actually the interior of the mouth. Well, it's not great. It's not every teeth is like super visible, but it's at a reasonable fidelity. And then what we did is we now go ahead and have this NPHM. It's this neural parametric head model. This is basically composed into two MLPs, one for the pose, one for the expressions, and one for the identity. And they're parameterized respectively, similar to the NPMs what we had before, by a latent code that controls each of these spaces, right? And then we have a learned representation where we're changing the latent codes. One of them makes sure that only the pose changes, and one of them makes sure only the identity changes. And what's very critical is that these two spaces are actually decoupled. And then at test time, we can fit it, right? So we have a depth observation, and we can optimize basically for these ZRD and ZX parameters, and we can optimize for those ones. And I'll go a little bit into more detail, but this I wanted to go first at the high level that you roughly get how we did this. Yeah, of course.
You decide how to break it up into different expression identity. Identity is often a little bit more complex in that, like, they could be hairstyle or things like that that are not affecting your identity, but are also changing and are not pose. Is that how did you make those decisions? Of how
yeah. So we'll get to this, and the way we did this is basically throughout the data that we used. So in our case, identity meant same hairstyle, no changes in anything else. So an expression was literally basically face muscles. So if I take you and I'm asking you, make 20 different expressions, like smile, look angry, like do a little bit like this, right? Yeah, and it's very controlled, and it has nothing with the hair. The hair does not change based on the expressions right now. And arguably, this is a big limitation we'll talk about. Like, this is not controllable hair at this point. Right? This is just, there's no style in the hair or something like this.
Does that mean pretty much same session in capturing?
Right. I'll show you in a sec. And what you're getting is something like this. This is basically, so you see here, these are just random samples in our space. So the point is, okay, the hair is still not perfect, but it's a lot better than all the previous models that were around. And you can go ahead then and interpolate in the space. So this is like how we interpolate in our face model. So you can have this shape parameter interpolation, right? You see that, both the face is changing, the shape is changing, but the expressions are staying pretty consistent here. This is kind of the high-level goal, that we disentangle this one correctly. Or on the other hand, if you're saying we're changing just the expressions, that looks like that. So here we're interpolating the expression code. These videos are actually in sync. PowerPoint, unfortunately, can't play them at the same time. But I guess you can see that it's kind of a nice, smooth parametric space where you don't have anything that doesn't look like a face in it right now. Okay, now I promised you a little bit of more details here. So we have to get a little bit into the technical stuff. So the way we started is we started with 3D scans. And with 3D scans, we basically had, for every person that we scanned, we had one neutral pose that looked like that, and then we had controlled expressions for everybody. We showed them literally a picture look like that, make that specific expression, and we had 23 of those per person. And then what we did is we had a non-rigid registration. So probably this is the hardest part you need to get right, because now you need pretty much perfect correspondences between the different shapes. So here we use an aura-based registration. That's like a non-rigid term that makes sure that you can align the templates from the neutral pose. Well, we first start with the template, then we use the neutral pose, and then we register it to every other scan that we've taken from the same person first. And then what we're doing is, once we have every person, we have perfect mapping to the canonical pose, we're mapping each person with respect to each other as well. So you need these correspondences, and from the student's perspective, that's where we spent most of the time on, which was the smallest part of the paper, but I think it's the most important one actually, because that made it work. Okay, and then I'm going to go in a bit more detail how the parameterization of the MLPs actually worked. It's not just one MLP that we used here. In fact, we used for the identities, we used a local ensemble of MLPs. So we literally took facial key points, and they look roughly like this. And for each of these key points, we have the distribution of these MLPs, and each of them locally have their own latent codes. And then we have a linear interpolation based on where you are on the face respectively. Yeah, and this is how you're getting the final identity by combining these local MLPs together. And then for the expressions, we took a single MLP for everything, because for expressions we tried that too, but expressions are more global. Right, so we argue that, okay, for the identity you need local detail, that's stored here. We also made sure there's a symmetry term, that they are roughly symmetric. Basically your faces on average are symmetric. And then for the expressions, we made sure we have one global one. We experimented a lot with that, yeah?
The identity MLPs are outputting deformation on the registered template.
Exactly. They're outputting deformations, which is literally an offset. Like, how do you... Exactly. So the deformation is just how do you need to look up in the canonical space the respective value, and the values we're predicting are sun distance values, actually. The one I should have mentioned too. Okay, so this is cool, and we spend a little bit of effort on engineering this. Like the registration I said was pretty tough, but I mentioned one little detail I haven't talked about the data yet, right? Because we need to train this model, and this data didn't exist, so we had to scan it. And the way we created it, we built this little scanner here. It looked like this here, right? So we have here a rig. This whole thing spins. There's a motor on top of it that spins the whole thing. There's two RTEC face scanners. This is like, we checked out what was on the market. This is for money the best you could buy in the commodity setting, while not taking forever to scan. And then they do have RGB, but the RGB looks not great. So we didn't use any RGB here. And the 3D scans look like that. So they look pretty reasonable. And then a scanning session looks like this. So this is the person here. They see the expression that they should make here. Again, we have these 23 expressions that they should make. And then we press a button, and then the scanner goes ahead and goes around twice. And then the scans you get on so this is me on the left, for instance. These are the scans you're getting basically every time. This is Simon. He's the lead PhD student who ran the project. And in total, what we did is we created this 3D head scan data set. In total, we have about 5,600 scans. We have 270 different identities, and each scan has about 1.5 million vertices, about 500,000 total frames here. And we actually released that data set now. So like this week was the week when we put it online, and we hope that people can now go ahead and also train their own models around it. Okay, so a couple of more results. So we used the data to train it, and I think it's kind of cute because this level of fidelity didn't exist yet. And this is what you're getting right now. Again, on the left here, you see the input point clouds. These are the existing methods. This is the ground truth scan, and this is our model, what it gives us. You see there's still a bit of a delta between the model fidelity and the scan fidelity, right? You see the hair here is a little bit more detailed. Hair is still challenging, right? This is a structured light scanner. So yeah, this is still improvable, but I think compared to what people used before, it's already a big step forward. You can do the same thing with expressions, right? So now again, you have a point cloud. This is what the respective baselines give you. This is what we get. Again, you can see the hair is not perfect, but I think at least we have some hair, right? It's better than nothing. what's kind of interesting is now we evaluated this whole thing a little bit. This BFM is spatial phase model. This is Flame. This is the standard NPM architecture. This is our architecture. And you see that with respect to chamfer distance, like how far away are you to the ground truth, there's actually quite a difference. So this is basically this 0.05, what we're getting here at the end is the architecture. And this one is just replacing the PCA with an NPM, basically. So this one looks pretty good in terms of quantitative evaluation compared to the competitors. We also tried like how robust is it with respect to how much, how many points do you need. So you see this depth input, we just varied the number of points we fed in here. Yeah, you see like you need at least 1,000 points to get a rough reconstruction, which is what most depth sensors would give you. We also evaluated a little bit how noise went. If you have too much noise in the depth, it breaks down, but it doesn't catastrophically break down at the beginning, which was important. And one thing we also tried, I didn't have it here. So it was interesting when we did the project. At the beginning, we didn't have a lot of scans. So the whole thing started working when we had like 60, 70 scans. 60, 70 people times 23, respectively. And now with like plus 200, it works actually pretty well. Here we are evaluating expression transfer. So you take the expression codes from one and copying to the other one. And then the idea is you kind of can reanimate the targets accordingly, right? So you take here the source and you transfer the expressions to the respective other ones. And this was really critical, right? Because these models are basically only useful as soon as you can very precisely decouple expressions and identities. Otherwise, they would not be very helpful. All right, so this was kind of cool. So this does, I think, provide a pretty good phase model. The only little thing is we have geometry, but no color, right? So I promised you we want to do photorealistic reconstructions and not just geometry, because ultimately we would love to fit this to an image. And well, the problem is this data set, these RTEC scanners that we had, they don't provide very good RGB. They do it, but they're not great. So now we need good RGB data. And coincidentally, we built in parallel another setup where we actually captured the RGB. So we built a capture setup that looks like this. This is a capture setup that has 16 cameras. Each of these cameras has 7.1 megapixels and they record at 73 frames a second. So they are high-end machine vision cameras. They're lucid, if you know it, like this is what a lot of people they use. And they have less than a microsecond time sync. So they're all synchronized. They have global shutter, kind of what the maximum we could fit in terms of bandwidth that we could still stream in real time, basically. And the idea here of this data set was that we did this actually in parallel. So every person that came into the first data set came also in the second data set. So we recorded them actually at the same time when they had the same hairstyle, the same cloth, and so on. And the recordings here, they look like this. So we have these, well, PowerPoint should play videos. Okay, very good, PowerPoint. So they have these ones, they're actually longer. I'm not sure why PowerPoint is failing here. But yeah, this is basically the videos that we're recording. And they actually have a pretty high resolution. So if you're looking at these, they look like this, right? So you can go in quite a bit and you see pretty much every hair here in the face. We also have a pretty high frame rate. So we deliberately wanted to go to 70 frames. So you can do stuff like that, right? So you can get like all the hair motion without having a lot of motion blur. This was quite important to us.
But this is not reflection functions, just the RGB.
This is just the input right now. There's no reconstruction. This is just highlighting, okay, this is like, we wanted to have a really rock solid data set here to start with.
But you weren't strobing the lights or anything?
No, there was no light. There was no, yeah, it's a good question. So we were thinking about doing that. We just have a uniform lighting. It's always the same, but we have no control over the lighting. So it's not a light stage at this point. I'll talk about this a little later, but yeah, the lighting is obviously one thing we don't care about. Well, we care about it, but we couldn't deal with it at the same time, basically. Yeah, so this is the data set that we have. It's this multi-view data set, so we have basically 16 views in parallel, and in total what we did is, it's a little bit lower than the other data set, so the first N people, we didn't have that one ready, so unfortunately, like the first 50 people were missing here. But we still have 220 people right now. In total, we have almost 5,000 sequences. The sequences are also controlled, so we tell them always what to do, so they're synchronized. It's about 31 million frames and about 7 hours, 30 recording time. And now the point is, what we wanted to do is we wanted to take that data and do first reconstruction. So in other words, we wanted to take that data here as input that we have. And from that data, we wanted to reconstruct what we have here on the right. So on the right, this is basically our avatar, our reconstruction that we have. So this is now novel viewpoints, and we can look at this one from any perspective. This is the nerve style reconstruction that you can look at from different angles. Okay, so what's the high-level idea? How do we get there from taking these as input and taking these ones as output? And at the beginning, we thought, well, this is straightforward. We're just going to run nerve, right? Because we have multiple viewpoints. We're going to take those, reconstruct the radiance field, and we're going to be all good with our reconstruction. Unfortunately, the higher quality of the data and the higher frame rate made this problem a little bit harder than we thought. And the problem is these MLP bases, like even for these neural parametric models, neural fields, what I mentioned before, they are really bad to scale. Like you can't just add more capacity and hope it handles more detail, unfortunately. We tried that, it didn't work. So our high-level idea was very similar to what we had before for the geometry. We thought, well, we're going to start with a dynamic 3D representation based on radiance fields, right? So we have density and radiance that we store at every point in space, and we still wanted to encode it in an MLP, though. But that one we want to do is we have this dynamic representation with deformations, and that one we wanted to map back to a canonical representation, right? So the canonical representation is looking always straight, but it still has to change slightly because it's not just a rigid mapping backwards. You're going to have local detail that changes, like when the eyes are blinking, when the mouth is opening. And this is what you saw here, right? So this one is actually changing slightly. Now, this is what a lot of other nerve papers have been done before. They were like papers like HyperNerve, well, okay, others like DyNerve, they did a little bit different stuff, but they had this, they followed the same concept, and we tried that out. And we realized very quickly, also this one didn't work out because we have relatively high fidelity sequences with relatively long periods. So you can do this for like 10 frames, you could do something like this, and this works, but not for something that has, let's say, a minute of video. And what we did here is we tried something like that where we said, well, we wanted to copy or imitate what blend shapes are doing actually. So we said, over this whole sequence that we have, we're taking a bunch of canonical poses, and we call them static 3D representations of blend shapes. They're not real blend shapes, they're just canonical codes. And what we want to do is we want to learn a blend function between those ones simultaneously. So the representation and the blending is learned jointly in order to create this dynamic canonical 3D representation. So it's not just one representation, it's multiple, and it learns how to reweight them. And each of these individual ones, they are hash-based encodings. So we have one hash-based encoding for every single one here, and that is optimized over the entirety of the data that you have. And the irony was, before we did have that, the more data we threw at it, the worse the results got, which is not what you want. You want the opposite. You want better results when you throw more data at it. And now we basically say, now with more data, we just create more of these static templates, and then it scales very well to more data. And then the method itself, I mentioned this is a nerve-based representation. You have this radiance field encoding, you do ray marching, right? You do volumetric integration, and then you can re-render. And yeah, so the first thing I mentioned is we have this MLP for the deformation field. I'm just repeating what was in the previous slide. I'm just going into a bit more detail here. So we have this MLP, that is this deformation field. And this one now accesses the canonical representation. And the canonical representation is a combination, a linear blending of multiple hash ensembles. This is like instant NGP for each of these static ones, but then it has to figure out how to reweight them. And this is this blending function that we're learning here. We call this feature blending. So each of these hash ensembles is a static representation that gives you a feature that is learned how to blend, and then it gives you the final feature for the output. And now this becomes scalable because we're now basically saying, well, each of these static hash representations, they're distributing the canonical poses, and they can remain sparse. They don't have to allocate everything. Yeah, and then we have this base MLP basically that gives us the radiance field, the density, and the colors as output, and then we can do volumetric re-rendering.
The blending functions, are they unique to the person, or they're
Yes.
across the data set?
Okay, this is something I should say. This is just per person right now. There's no generalization whatsoever. This is just optimized for one person. And And the point, though, is that the sequences per person can be relatively long. And the point is, if you don't use something like that, you're not going to get you're going to get worse with the more data you throw at it, because the MLP runs out of capacity and it gets blurry, right? And so what you have to do is you need, like, for every kind of pose, you need one static hash ensemble, basically. That's how we solved that problem.
How do you figure out what the blending functions are?
Well, the blending function is linear, but the weighting is learned.
Okay.
So we don't know about how to blend it. But we just, our re-rendering objective is always make it as photorealistic as possible. So we have 16 views, right? We have the whole sequence, and we just, across these views, we have the reprojections, and they tell us, like, how, based on the reprojection, they tell us both how the hash ensembles have to be learned, the deformation has to be learned, and the blending function has to be learned. And this is all simultaneously done. But it's a lot of data per person, right? Because you have these 16 views, basically. Okay, we don't have 16, we have only, I think we used 13 at the end because we needed test data too. So we tested them on the other ones. Okay, and if you're combining all of this, you're going to get reconstructions that look like these. So they look actually, I think, pretty decent. So this is, I would say, probably the state of the art what you can get right now. By the way, this is not laggy. This is PowerPoint not being able to play 5 videos at the same time. Okay, and we have a bunch of baseline comparisons here. So I hope you can see that. It's a little bit tricky to see, but so is there actually a way to turn off the light at the front? Is this possible, maybe? Okay. Oh, it's turned to me?
I'll try. You do. You continue. I'll try.
Okay. So, oh, here? Because then you can see it. Oh, thank you. All right, that's already much better, I think. Okay, so here you can see basically, like, if you look at, so NERFIs was the standard one that people were using, that's using MLP for the deformations. Like you see here, like DINERF was the best one here, but you see the hair is like not very, it's very blurry here. Like look at this hair compared to this hair what we have here, right? It's quite a difference in fidelity actually. The other thing what a lot of people said at the beginning was, well, why do you do this with the deformations? Why don't you just optimize a NERF per frame? You can actually do that. So if you're running per frame instant NGP, you're going to get something that looks like that, right? You see these temporal artifacts over time. This is a per frame NERF reconstruction with a state-of-the-art method. And then, yeah, if you use ours, of course, then we don't have that issue anymore. And yeah, but I think it's pretty good fidelity, right? So you can go, you can zoom in pretty much, and I think these are pretty decent reconstructions that you're getting actually at the end of the day here. A couple of ablations. Here we're trying to evaluate, do we need all of the stuff? So we have here, at the beginning, we have the ground truth. This is from our data. Here we have just instant NGP plus a deformation field. You see that it's, the teeth are very broken here. Here the hash ensemble looks already a little bit better. The deformation field looks also better, a little bit. If you're combining it with we have a bunch of special training, then it looks like that. And then if you use the final one, then it looks the best. I hope this is visible on the projector. So this one it's still not quite the ground truth, obviously, but it's relatively close. Okay. The one thing what is kind of cool, obviously these are not actual blend shapes, right? We just derived that from the face models because we thought this was really cool work. So what you can do now is you can change these blend weights that were learned. You can actually change them manually afterwards, and they have some meaning. So they're not perfect blend shapes. They're not all great, but you can change them, and you get these kind of results that closes the eyes, opens the mouth slightly, and stuff like that. And we didn't investigate this further, but I think this was kind of cool that our intuition of having these static templates would actually encode important kind of key poses. This actually worked pretty well. Yeah, I think overall this looks pretty good, but there are still failure cases, of course, right? This is not a solved problem. And so we're going to release the data in the next 2 weeks or so. It's definitely before SIGGRAPH. This is a SIGGRAPH paper from this year. And like this hair motion, what you saw before, this is still not working very well. And the reason is very simple, because this deformation field is not high enough in terms of resolution to capture every hair strand. And I think this is kind of cool, and I hope that people will look into it, and we will certainly also look into it in trying to solve these kind of things. All right. Okay, so this is something we've done for faces. Now, question is, can we do the same thing for humans? And well, we do the usual thing. What we do is we check out what data do we have. So we wanted to get some data for a full body with multiple cameras, and we captured some data, what we usually do. In this case, we have a data setup that looks like that. This is, it's a capture studio. It's called Infinite Realities. So they build these things professionally, and you can rent them out, and that's what we've done. In this case, this is, it's a data set of 8 actors, 16 sequences, and about 40K frames. So it's not that long in terms of the overall time, but the setup has 160 cameras. Each camera records at 25 frames a second and 12 megapixels each. And per frame, you get the RGBs of each of the cameras, and you get the ground truth mesh. Also, the lighting here is also constant. There's no lighting. We're working on the lighting right now. I mean, that's kind of the obvious next thing. But like this one is still consistent lighting. And this data, I think, is probably the best what money can buy right now for these types of recordings. So their setup is called Deus Ex. It's like their capture rig. And they spend really a lot of effort getting really high fidelity data here out of it. I could zoom in even further here. This looks like pretty rock solid. And then the recordings look like this, right? We hired a bunch of actors. And these actors were, performing certain things, mainly dancing a bit, moving their hands, and looking good. And then we captured this data, which is looking like that, right? So these are the different cameras that you're seeing here. And yeah, and then for each frame, we also recorded the we reconstructed the respective 3D meshes. So you have pretty good multi-view stereo reconstructions on a per frame basis. And yeah, and in total, we have these 8 actors actually that we recorded. So yeah. So they're standing in this platform in the middle while they're being recorded. I wanted to quickly also show how the 3D reconstructions look like. So this is a textured 3D reconstruction now. So this is not textured, but like the images you saw were from these views. So you see even the multi-view reconstructions on a per frame basis. This looks pretty decent here, I think. And now what we wanted to do is we wanted to take that data and do the same thing what we had done for faces. We did, however, do a slightly different method here. So the method that we used here was actually more based on TensorRef. But it's the same problem, basically. The amount of data doesn't allow you to do this with a single MLP. And the more data you throw at it, the worse the reconstructions get because you run out of capacity in your MLP and it doesn't scale. So what we're doing here is actually, so there's 2 parts of the method. One part of the method is the spatial segmentation, the temporal segmentation. So we have segments temporally that we adaptively subdivide based on how much capacity we have. And then for each segment, we're having a temporal decomposition based on TensorRef. And the way it works is 3 dimensions are based on hash ensembles. And then we have 3 times 1D fields on top of it that do this TensorRef composition. So we have multiple decompositions here, right? In this case, and each of these ones then have this 4D TensorRef decomposition. It's like a temporal decomposition. The closest work that came out recently that does something similar was Nerve Player. They do a similar thing, what we do, except that their goal was slightly different. They wanted to have it for streaming. We wanted to have it we wanted to get the highest quality. We don't care how fast it is right now. And if you're running all of this, you will get reconstructions that look something like that. So this is a reconstruction of 1 frame. And we can animate the whole thing now. So these are the results of the method that we're getting at the end here.
So I'm not sure I understand fully how you're animating right now.
There's no animation.
Okay.
It's just replay at this point.
Yeah.
This is all baked in right now. Yeah. That's the obvious next step now, how to make it animatable. Yeah. But it turns out even this, the pure reconstruction and have like this like 4D video, so to say, is actually really tricky. And even right now, if you're looking very closely, I mean, you see that, for instance, here the hair and stuff like this, is not perfect. And we threw a lot of money at this data, actually. Like, we try to get really good data. And it turns out, like, this is still very difficult to get perfect reconstructions. And I wanted to talk a little bit about how to fix these imperfections, because we have one project that we tailor this. This is not just a problem for dynamics here. This is a problem you're going to have for everything. You're going to have the same problem also for standard nerve reconstruction. So if I take n images here, and I take like what Angie was talking about yesterday, even if you have high quality data, you're still going to have some imperfections, no matter how much effort you spend. So this is actually an example scene of the ScanNet++ data set that Angie is collecting right now. So you see that this is very good data. This is high-end DSLR, and we try to capture a lot of images here. These are, I think, 2,000 images for this space. And it's still not perfect. And if you're playing this quickly, you see this you see, for instance, here the text at the bottom here is not perfect. It's a bit blurry, right? When you're zooming in, you have a bit of flickers. And again, that's the best settings. And we asked the nerve folks, what's the best setting to get good nerve reconstructions? And yeah, that's the best you can get. It just doesn't get any better. Like, more data doesn't help you at some point anymore. And the question is, generally speaking, and the same counts for the dynamics, right? So this is very agnostic to the data you have. You're always going to have some floaters. You're going to have some blurriness. And the reason is very straightforward why that happens is, I mean, nerve is a multi-view stereo reconstruction problem, right? It's actually no learning problem. It's just an optimization. And this optimization, you're going to optimize and optimize and optimize, but for some regions, you don't have enough features. If you're having a white wall and want to do stereo matching on a white wall, it's very tricky to get good depth estimates. And it's the same problem here, basically. So the question is, how do we fix the nerves? How do we fix that? And the easiest thing you can come up with is you take a nerve, you use nerve as is, you render stuff, and then you run a GAN or so something like this behind it. It's called neural rendering, but neural rendering is nothing else. You have a discriminator, so you have an image, you render that image, you have a conditional generator on top of it that says, please make sure this kind of okayish image will look perfect. And the way you do it is you're simply sampling like nerve patches, and you're comparing these fake patches with real patches from the real world, and you're trying to have this generator try to bridge the gap what's still missing here. And this is not a new idea. People have been doing this. Pix2Pix was the first that did this. This is like this famous paper from Philip Isola. And the challenge with that is very simple. If you're doing this with a nerve-based reconstruction, you unfortunately won't get temporally consistent results or few consistent results. Right? The problem is, like, each image will look reasonable, but it has no temporal coherence. And what we thought is, well, maybe we can take the same idea, but backpropagating actually these discriminator constraints back to 3D. And by back to 3D, what I mean is you're taking this multi-view RGB input, and you run standard nerve, and you're optimizing for the nerve parameters. And in addition to that, now you sample from patches from the image is of that scene, and you say everything that you render ever at the scene has to be that real distribution, which is neural rendering. But except that having a 2D generator, we're just optimizing the weights from that nerve further. So the weight nerve now have two constraints. They have patch-based constraints from a discriminator plus the standard nerve constraints. And the way this works is like this, right? So we have this 3D feature grid. We have nerve. We do ray sampling. They are stored in an MLP. We have density and appearance predictions. We do volumetric rendering. We render patches out of these ones. From our multi-view RGB input of our static scene, in this case, we do patch sampling. So we get a bunch of patches here from the real distribution. And now we have a discriminator that compares these two basically and says, hey, am I real or am I fake? And then you're going to backpropagate through the whole thing. So there's no generator in 2D, right? The only thing that exists is an MLP that stores the radiance field in 3D. And the point here is also that this discriminator doesn't generalize. It's just optimized on one scene. It's just for samples of this one scene. And there's a few tricks you can make this work actually better. For instance, in one mini batch, you want to make sure that you have patches that see the same stuff, but from different viewpoints. Because then you get stronger gradients in this patch sampling that help you to optimize for the 3D stuff. Yeah, and then, I mean, the final loss is basically like this, right? So you have the nerve loss, which is the standard RGB loss. We're using a perceptual loss as well, which is used in pre-trained features. And then we have this discriminator loss that we're having here right now. And then we just optimize for the respective 3D radiance field. That's That's the only thing we're optimizing. Well, okay, we have the discriminator we're optimizing too. The discriminator is also per scene based. But then you backpropagate all these constraints. So the idea here is basically now, if I have a scene where you have a white wall, okay, I don't have good multi-view stereo matches, right? It just doesn't give you good gradients. But you're gonna have these patches. They have a discriminator and tell you they have to look white no matter from which perspective I'm looking at. And if I have a viewpoint right from here, that would be very creasing angle-like. You can't create a floater in front of it because then this patch in back there would not be a real patch anymore. Yeah, and if you're doing that, you're gonna get results like these. So this is ground truth. I think this is from Tanks and Handles actually. So this is ground truth. Nerfacto is like from Nerf Studio, basically the latest one that is released. That's one what we used here as a baseline. And then we're adding this discriminator. And you see that the discriminator here fixes a lot of stuff, right? So a lot of these things here are actually being fixed then afterwards. OK. And yeah, we have another example here. Oh, PowerPoint is amazing. Wow, that was too fast. OK, so here we see also the chair, right? At the beginning, it looks like this. And then afterwards, with the discriminator here, it looks like that afterwards. Yeah?
So if you take your finite capacity of your MLP and now allocate some of that to satisfy this additional discriminator objective, are there areas where you lose some fidelity on the original objective?
No, because in this case, there's enough capacity with this with the standard MLP representation. Like this is the reason why NERF doesn't look good in this case on a per scene reconstruction is not because of lack of capacity. It's literally because you have regions with not enough constraints. Yeah.
So I thought of something like this, but my concern was the discriminator couldn't be trained because you have very few patches from that one scene. So did you simplify the discriminator?
No, it has to be a pretty powerful discriminator. So we use.
You're able to train with just the samples from that scene.
Yeah.
Basically to overfit the discriminator.
Right. The scene has to be large enough, though. So the scene, if it's just like like a single box or so, it wouldn't work.
Like a single room, like it has to be enough.
If it's a room like this, it works well. And let's say for this room, you have like I don't know, let's say 500 images for this room, which is this is not targeting low end. This is targeting high end in a sense, right? Then you have enough patches that it actually works, and you can do a lot of augmentations there and various ways how to do sampling, and then it starts working. But yeah, the scenes have to be reasonably large to have enough of a distribution. In principle, we would like to generalize this discriminator.
Yeah.
And there's a little bit of an issue here. The problem is if I take n scenes from a larger data set, this discriminator will learn which scene it is. It will check, oh, is it from that scene or is it from any other scene? And we tried that. It doesn't work. Then it's going to say everything from my current scene is fake because it's from that scene. It just classifies the scene. It's a really annoying issue. So the way to fix it would be you have to train a NERF on all scenes simultaneously and then have fake patches from all NERFs from all scenes at the same time. And you can imagine this is a lot of compute then, right? This is not so easy to tractable. We haven't done that yet. It's something we're considering, but I'm not sure if that's the right way to go. But yeah. Okay, a few more examples here. Yeah, discriminator fixes these high-level structures, which is nice. Fixes also like structures like these. And yeah, here's a bit more here, right? You go from here to here. And you go from here to here. So it looks pretty good. So this backpropagation here from a single scene discriminator works. So you can optimize it on a single discriminator. It helps to recover the structure. But being a critique here, this is still not perfectly sharp. I mean, okay, it's zoomed in quite a bit, like this is the original image. But it's still not perfect. And then we thought, well, why don't we try to make sure we fix local features? And the way we do it, we just have a neural renderer on top of it. So we're trying to have the neural renderer that fixes the discriminator that backpropagates to fix the 3D structures to the best of the ability. And then we're adding another discriminator on top of it afterwards. We're adding a generator on top of it afterwards. It's actually also a generator that is, again, trained on a single scene, and it's a multi-scale discriminator. So we have all these scales here, so we downsize it. We're feeding this multi-resolution input right now in this generator, and then we have rendered patches now again, and we're comparing these with a second discriminator with patches from the real scene. and then deciding which one it is. This second part is kind of inspired from SYNGAN, right? So they did this on a single image, and we're trying to do this on a single scene right now. So it's very, the second idea is very much the same thing, kind of tailored towards this nerve optimization. Okay, and it turns out this combined makes it even better. So if you're having this, now we have this second loss function again, we have a perceptual loss, we have an RGB loss, and we have the adversarial losses here. This generator is also pretty much a StyleGAN-based discriminator, and it uses this multi-resolution. So it goes from different levels. And this is also critical. Without this multi-resolution stuff, it also didn't work at all. This was not that easy to train, actually. Actually, sorry, the training was easy. It was not so easy to find the right architectures for the hyperparameters. But once you have the right hyperparameters, it actually works pretty much in any scene. So this is kind of funny, yeah, but this is how GANs go, I guess. Okay, with discriminator, it looks like that. And then at the end, it looks like that. So it still adds quite a bit more fidelity here, actually. So you can see here, this is the same. And now,
do you compute an altogether new image, or do you compute like an error, like a residual that is tacked onto the previously synthesized?
Yeah, that's a good point. We actually compute a new image. We thought about it using it as a residual too. It didn't make a difference, actually.
Really?
But I should say, in fairness, this is something we did at the end, so we could have probably played around with it more. I thought also that this would help with the residual image, but
It's almost like a simpler problem of like fixing it as opposed to take this.
Yeah, exactly. But it didn't make a big difference, actually, which was interesting. Yeah, I mean, in all fairness, like again, finding the right architectures here was not that straightforward. This was probably the hardest part. Like, it sounds maybe easy, but it's not so easy to get it to work. But yeah, here's a few more examples, right? So this carpet at some point looks even a bit better. It's still not 100% perfect, but if you're looking at on the very left-hand side what the input image was, or the original resolution, that's quite a difference. Okay, so the quantitative comparison here we did on Scan++, which is the scenes what we had already. So this is basically what Angie's group is scanning right now. We're comparing here PSNR, SSIM, LPIPs, and KID. We have this one when we just take the 3D stuff. So this is kind of funny. So if you're only doing that, the PSNR gets better, but not that much better. And the reason why it doesn't get that much better is the images itself, the PSNR is basically a logarithm of an L2, right? So L2 doesn't measure sharpness. That's why this is not measured here. And the other thing what happens is some parts, I mean, it's not happening at the dramatic scale, but you could imagine that at some point it might hallucinate local detail that is 3D consistent, and it looks good because it forces it to make realistic patches. But it didn't see those patches in the input. So on these ones, it wouldn't have been evaluated, right? So this is why this is not that dramatic, but PSNR is a bad metric for that, basically. That's what I'm trying to say. But everybody uses it, it gets better, and it's important to look at. But obviously, like if you look at the perceptual metrics here, like LPIPs or KID, massive difference, right? It makes a big difference. If you're adding now the discriminator on top, it gets, again, quite a bit better, right? Like it gets from, like KID and LPIPs are, I think, the most notable one that changed the most. And you see that perceptually speaking. So we looked at it, we also did user studies, having people look at it, and this is actually clearly better. These were not cherry-picked results. They, on average, look a lot better. We also compared against all combinations of like Nerfactor and Instant NGP and stuff like this. So we tried Nerfactor with pix-to-pix followed. That one didn't actually work at all. Like this one didn't help too much here. And the reason why that didn't work at all is like these, first of all, the architectures were not the right ones. We tried also more capacity. We played around with that. So it only worked basically if you have this 3D back propagation first. That made the biggest difference in the end of the day. You needed that, otherwise it didn't look good. Okay. Yeah, I'm coming slowly to an end, so I should probably move on. Here's a few more examples on tanks and temples. Yeah, this is ours. This is the baselines. I guess you can clearly see that this one looks a lot sharper here. Here you see the chairs. Also, this looks also a lot sharper. This one I think we've already had. Right? You see here, you see all the detail here on the chairs, whereas here you didn't see it at all. And you see this with MIBNERV 360 we have as well. And then I wanted to show the scene from the beginning again. This is the video right now that we can render out with that, and I think this looks actually not too bad from an output here. And you see here the difference on the left is Nerfactor. Like look at the at the first aid kit here or the fire extinguisher, right? It's quite a noticeable difference right now.
But it's not as fast anymore because you need that post-neural rendering step to apply.
Yeah, but it's like a few milliseconds. It's a forward pass. It's like two milliseconds. I mean,
Really? Okay.
yeah, yeah. Like from a nerf rendering, it makes almost no difference. The nerf rendering itself is the bottleneck.
I mean, there are accelerations there that you might think about applying, but...
Right. Yeah. I mean, I hope it's visible here too. On my screen, it looks very different. Right? You see like these buttons and stuff. They look very different and so on. Yeah. There's another scene. But I think we're getting there to make this photorealistic, right? It's not that far off anymore.
Seems like appearance really makes a difference for the material.
Yeah, especially, so materials are really tricky because there you have not just a 3D function, you actually have the angles of the nerve too, so you have a 5D function. That means you would need more constraints to fit it properly. Yeah. This is why the specular parts here make a really big difference. So like, if you look at the computers here, yeah, or like, on the floor here, this is one of our labs that we have. Like the keyboard and the outlets and stuff. I mean, it just looks really a lot better now. I think this is, from a nerve perspective, it's among the best nerve methods now that are working. Okay. So yeah, we've done this on 3D scenes. Obviously, we would have liked to combine this also with the dynamics that we have seen before. We haven't done that yet. But this is still, I want to go back to that one, right? The reason why I wanted to show that this is just a standard thing that you can plug into any nerve method. I think, generally speaking, like these like discriminator-based methods, combining them, this would still make things a lot better. Like, I think also the diffusion models could work a lot better here. That's, in fact, what we're doing right now with that data. But the big thing what we're trying to do for these 40 avatars, we're trying to learn to channelize, right? All of the stuff you have seen right now was all one scene for the models that we have. These reconstructions you have seen on the humans, per scene optimization. For the scenes you have seen right now here, per scene optimization. So how do we channelize these ones? This is what we want, right? We want to sample from a distribution and get a new person out of it. And ideally, we would like to then take a single image as input, right? And then reconstruct this thing perfectly. And then animate it and have an avatar around it and do that. So there's still a lot of things missing here. And I think we are still just tapping into it. And it's still very much at the beginning, in fairness, right? I know there's a lot of nerve papers and stuff like this coming out every day, but I do believe that the quality is not at a level where an end consumer would really appreciate it. So there's still a lot of things missing. Yeah, the channelization, we have the data set right now, right? This is what we're working on. We have these 200 plus people. We have nerve reconstructions of each of them. So we do the obvious things. We're training diffusion models right now to try to channelize it. That's, because that's what people do. But we have to be also a bit honest, right? It's just 200 people. So learning a channelizable model that can create new people out of a data corpus of 200 people, that's not going to work. Like, we have no illusion there. We know that 200 people is not enough. And I think this is a very fundamental question, and I've talked with a lot of people already around this, is like, what data do we actually want to use here, right? And so what we have been doing, or what I've been showing you in this talk, we've done a lot of high-end data capture here, right? Like very, very high-end, high-quality cameras and stuff like this. But it's not all what we can do. We have a lot of different modalities, I think, right? So this is what we have done, multi-view 3D. You can scale this to thousands of training samples, right? Or thousands of people, maybe thousands of scenes. Maybe Facebook or Google can do it for 100,000, but they can't do it for 10 million. No matter what, right? They can't do it. Nowhere near. For videos, you have millions, maybe a billion if you take all of YouTube or whatever, right? Images, like Lion has billions, I think. How big is Lion? Like 7, 8 billion or so, I think? 5 billion? Okay, yeah. Text, you have trillions probably, right? Like sentences you have to train on. But the thing is, right, I mean, the whole point is this one has more training data. The text has the most training data, but it has per sample the least signal. So this one has more supervision on the top. And I believe there's room for all of this, actually, and we need to make sure we combine that. And I think that is, in my opinion, what's really exciting right now, since we're seeing all the communities like, NLP, vision, graphics, and all of these communities, they're merging in a sense a little bit, right? So LLMs are pretty obviously cool. Can we extract these kind of things? Can we extract some priors for people from LLMs, for instance? And I don't want to go into the details, but I wanted to show you one small project that we did on the other end of the spectrum, where we only use text as supervision. So we have this project called text to room. So text to room means we just take text and we do kind of like knowledge distillation of stable diffusion, right? So you can create real 3D scenes pretty much just out of text. But if you're looking, so it looks pretty cool. But if you're looking closely, the balls are a bit bent, right? It's not the same fidelity what you had seen before in the scans. So it comes at a cost.
But you needed some example rooms to scan it or something.
Well, you just generate image by image, and then you do a reconstruction out of it. So you run stable diffusion, you get an image, right? Then you run stable diffusion again.
Then you get a completely different room.
No, but you have to inpaint it, right? You take the previous one as condition in the next one, so you can do some smart knowledge distillation there. We do a lot of stuff to make this actually work. And there's a bit of it. It's kind of like what Dream Fusion did on a single object. We're trying to do kind of for a whole scene, and we're getting a mesh out of it. But it's not perfect. It's not like the walls are not perfectly straight because the inpainting is not perfectly consistent and stuff like this. So there's a lot of issues with it. I think it's super cool, but it's like, it's not. And if you can go into this 3D scene, I think it looks reasonable. I think it's kind of neat. So this is on the other end, but you see the ceiling is broken, right? There's so many issues, and this is not like somebody you could put in a video game yet. But it's awesome. You can do this. A lot of text to image pairs in this case, right? So this is I don't know. I'm very excited about this, having the different modalities of the data, how do you mix it and how you combine it, and where you are. And I think I don't know. You need some high-end priors, for instance, planes, materials, BRDFs, decompositions and stuff like this. You want to have, or even the face models, right? This helps you for some parts, and for other parts like generalized identities, you need more data again, right? And I think this is what I feel is super interesting from a community right now, because we have all of these tools available. We have a lot of pre-trained models that you can use right now. They're free, and you can do super cool research on it. Okay, with that, I'm unfortunately a little bit over, but I'm at the end of the talk. I would like to conclude. These were a couple of papers that I've talked about right now. They're pretty much from this year. And I should also use a little bit of advertisement. We have a bunch of positions open. We have intern positions open. We have PhD positions and postdoc positions open. So if you're interested in any of these things, please let me know. I would also like to thank all the people who did the work, actually. There were a lot of collaborations here, of course. These were all the people involved. The people in the top row are the PhD students, actually. They did all the hard work. I'm just here talking to them. So I was fiddling my slides together today in the morning from the students. They sent me actually the content. It's not that I made this all up. So they're actually doing all the work. And of course, I'm very happy for my research team that spent really a lot of effort on these things and worked really hard for it. Yeah, so thanks a lot.
Thank you so much. It's very exciting work. So questions?
There was one thing I didn't understand about GAN-NERF, which is if you're training on a single scene, it's still a relatively small set of images. So how come the discriminator doesn't overfit or doesn't memorize the images? Yeah.
So you have, if you count it, right? So you have a few hundred scenes, a few hundred images, let's say 500. And you crop small patches out of these, right? You're on the order of close to 100,000 patches in practice, because you have different crops, right? And you randomly sample each of them differently. Each of them is a different crop. And that's why you don't overfit.
I see.
Right? You need enough images. If it's just 50 images, this wouldn't work. But for you can train GANs on hundreds of thousands, 100,000 samples. This works pretty well.
Are there scenes where you would expect that to break down, with a lot of self-similarity or not very much texture?
No, I don't think so. If it's too much, yes. But you have to think about it. The fake images would also have a lot of self-similarity, right?
Yeah, that's true.
It's just the delta you have to learn from the fake patches to the real patches. Even in this case, right? It has to, even if you have fewer images, you would still have a lot of like you have a lot of similar images from the fake ones, right? So it can't easily overfit that much because they are still very close together, right? But yeah, I do agree. Obviously, it's an issue, but you can tweak this with enough augmentation and with enough sampling of that.
Maybe you could regularize the discriminator too.
It is. You don't need it regularized that much actually. It's kind of funny. Like it's very interesting. You just need to sample it correctly. The sampling of the patches is really key, and have enough augmentation on the patches, then it works. But for like a regular room, let's say 500 to 1,000 images, it works pretty well actually. Yeah.
I really like your analysis of the. Oh, sorry.
I really like your analysis of the different bandwidths, almost of like the lots of content but very little supervision, and little content but lots of supervision. It seems to me like the ones that you have the high quality ground truth, you're using it to get strong priors and things like that. Can I hear your thoughts on how to embed those priors into the lower ones, because that seems like the natural direction. So how do you quantify these things so you can embed them into these more general
Yeah,
things?
absolutely. So imagine the following, what we have done in the ScanNerf work, right? So GANNERF was trained on a single scene, and you can already learn a reasonable discriminator to help you to get gradients, to get sharper images. So let's just say, just purely this, from a little less sharp to a little bit more sharp. Just this little difference. So if you imagine doing this in this text-to-room, what I showed in the end, you can pretty much already do things like straighten. I mean, this was a mesh now, but you can think about like, okay, learning to straighten the walls, making sure you have hard edges and stuff like this, corners. I think something like this you can very easily learn, and GANs might not be even the right thing there. Maybe the diffusion models. If I train a patch-based diffusion model that tells me, oh, this is the patch distribution that I have, and I make sure that all the meshes that I'm generating, they generate patches that look like that, then I can get the high-level structures of the rooms I get from the text models, right? Because they just have so much more content and diversity. But like the local details, like the sharpness and so on, that I think I couldn't get from the high-fidelity data. And this is how I'm imagining like using these priors from the high-fidelity data and then incorporating them, for instance, in these models. Yeah.
One thing we considered here was, because people can describe a room in words, they can also draw a simple floor plan, because it's actually pretty easy for a human to like draw the floor plan of your kitchen or something.
Right.
Have you thought about other alternative inputs to help guide the process?
Yeah, actually, that's a good point. Actually, this is something we have done here on Text-to-Room as well. So we have actually gone ahead and used floor plans, but it was very basic. So this was like one iteration people asked for it, what we should have done. And I agree.
I was a reviewer on that. No, I'm just yeah.
It's okay. But we did it actually. And what we did though is it was very basic. It was basically you have a floor plan, and this floor plan is how we selected the views and the respective prompts for these respective views. So the prompts in this case were then auto-generated from the respective layouts that you had.
So you almost had like a rendering problem where you'd rendered words from a view as opposed to, that's kind of cool.
But there's one drawback of that. It's not precise. You can't just say, oh, there should be like 5 centimeters, like look at this room here, like the spacing between the chairs or the seats. That one you don't get. So you get something like, oh, you have a kitchen counter and stuff like this. If you have this in your floor plan, then this works. But it's not going to give you a precise arrangement. And I do agree, but I do agree that this is actually a really important problem, because I'm imagining this to be used for like content creation tools at some point, right? So an artist wants to do that, and they need to have more control than prompt engineering. Prompt engineering is...
Words are okay, but you can't describe everything with words. Yeah.
Right. It's like spatial arrangements is very difficult to do.
Yeah.
Right. And I think, I mean, generally speaking, like, I don't know, just tell like ChatGPT something like how a spatial arrangement looks like is difficult, right? And yeah, but I think that's exciting. Like that's where the graphics and the vision folks can fully contribute a bit.
Any more questions? Maybe last one.
Yeah. Hi. So I have a question about the scene representations you're using. So underlying these methods, I see like a lot of nerve-based approaches or MLPs on canonical volumes. Do you see could you speak to like why these are so fit for these tasks, and do you see like any other scene representations being used in the future?
Yeah, very good question. So the way I see an MLP, for me, is nothing else but a data structure. So to me, like, I have a problem. I have a volumetric space, and I have kind of a voxel grid. I want to store my voxel grid. So if I store this naively, right, I have like a cubic memory consumption. But the problem is, of course, the surface detail and everything is just very localized. The next thing what people have been doing, like, is all these data structures, like you can use an octree to make it more efficient, right? You can use a hash encoding to make it better. Has nothing to do with neural networks so far. But all of these things people have developed, like the graphics community, like acceleration structures, like all of this kind of stuff has been around for a while. And these things work here too. You could replace an MLP with a hash-based encoding as well. And I've done a lot of work on like we had this voxel hashing paper a while ago, which did that, like using signed distance fields stored in hashes. And this works reasonably well. The one thing where the MLPs are really shining is they're differentiable. So when you have to make a discrete choice whether you subdivide or not, like for instance, if I have an octree and do a subdivide or not, right? This is a discrete choice. That's a really terrible optimization problem. But an MLP is very nice. I just have n capacity, I have a continuous gradient descent, and my MLP weights are being distributed to the detail or to the constraints that you're adding based on an SGD solver. That's why MLPs are so heavily used for nerve-based problems, right? You can replace the nerve-based representation with a voxel grid that is stored in a hash, right? I mean, in fact, the instant NGP try that and combine it then with an MLP. But this is doable, but the optimization is really difficult, because of this discrete nature of like volumetric building blocks that you're subdividing, right? And I don't know. I think so far the MLPs are great, but if you find a better solution for that, that would have a lot of impact, by the way, because that's like just so natural for these things. It's differentiable. It's very sparse for high-dimensional problems. Yeah.
Well, thank you so much again for a great talk and inspiration.
Yeah, thanks a lot, everybody, for the nice discussion.